too much mathematical details or anything. For you just to get like a general idea about topic of adversarial attacks in general, and about the thing that I was working on for the last 1 or 2 years on this type of specific adversarial attacks that are following 3D physicality or 3D data structures. So I'm a PhD student from KAUST. I work on computer vision. My advisor is Dr. Bernard Ghanem. Our group publish frequently on like CPR, ICV, ECV. And recently we started even working on like iClear, NeurIPS, and other machine learning conferences. We do works on computer vision, video understanding, 3D understanding, and fundamental machine learning understanding. This is my website, my Twitter account, and my GitHub. If you want to follow me, I also like publish useful general stuff about deep learning. Yeah, so you can find useful stuff there. This is my group on the right, and this is Bernard Ghanem in the middle. We do, as I said, we do a lot of cool stuff in KAUST, and specifically our group, and mostly focused on computer vision. This is me also with Jan LeCun. I guess you're familiar with him. He's the godfather of deep learning. This was actually this year. I met him this year in February in New York, where I was attending the AAAI paper. I was attending AAAI to present the paper that I'm going to present today, and he was a keynote speaker at that conference. So besides that, I also I work on the side on Fahm.ai. This is like an Arabic online platform to teach about AI. We do tutorials, we have a YouTube channel, and we do articles, videos, tutorials, codes, everything about AI. It's dedicated for Arabs communities, but who knows how it will go in the future. It's growing pretty good in a single or like 2 years now. So everyone now talks about deep learning, and like everyone says everything going to be done in deep learning. I have a saying, it's called like, you have to learn to do deep learning, or deep learning will learn what you do. So yeah. So all of this almost started because of the ImageNet challenge in 2012, when the AlexNet was introduced from right to left, and you can see the huge jump in performance led to so many in computer vision to use deep learning, and subsequently other domains like graphics and NLP started using deep learning. And now we see biology and probably geology and everything. Most of the fields will start to use deep learning because they realize the potential, generalizability, and the performance is just better than everything else. It's just like that. However, there is always a dark side or there is always, let's say, like a gray area in anything that shows huge promise. And in deep learning, the gray area or the dark side of deep learning is what's known as adversarial attacks. It's basically that it's very good, but it can fail miserably, very easily. And this is what we call lack of robustness. So this is like a typical example of adversarial example. You just add specific noise. It's very small, unnoticeable. You can see on the right, it flips the prediction from panda to like gorilla or like gibbon. And since that was shown in 2015, this direction of research, adversarial attacks and adversarial examples and adversarial robustness, opens up a huge research direction. Thousands and thousands of papers have been published on this topic, because this is basically one of the weaknesses of deep learning. And people have even showed that it can work on real life. So you print specific pattern real life, and it can fool state-of-the-art object detectors like YOLO version 3 or Mascar CNN or whatever. So this is not only theoretical things like we do on images, it can actually affect real life scenarios, and people have shown that it can even affect like line detection in self-driving cars or so. So this brings me to like a brief cover-up of the literature for adversarial attacks. So in adversarial attacks, you basically try to minimize, you try to find an adversarial example. So in all of this presentation, all of my papers, X would be referring to the clean image. For example, it would be this one, and this noise is the delta or X plus delta, delta, and this would be X plus delta, or sometimes I'll call it X bar. This is like the corrupted image that will fool the classifier. So how they do it, they usually minimize this specific loss, where you basically try to minimize the distance between the epsilon or X bar and X, and also maximize a specific loss, which is the opposite of the cross entropy loss that we use in training the deep neural network. So one of the earliest and most successful attacks is what's called gradient sign method, and this basically looks at the gradient of the loss. So you look at what is your loss, let's say cross entropy in classification. Instead of minimizing the loss, you actually maximize the loss. You take the gradient that will maximize the loss, and then you add that gradient with respect to the image, you add it to the image. And this X bar will actually be an adversarial example. A more common way right now people do in adversarial attacks is what's called iterative gradient sign method, where they basically, you clip this sign of the gradient, and then you do it iteratively. You keep doing that, let's say 20 times, and then you reach an adversarial example X bar T that works effective on any network that's defined here by F, let's say. There are other ways to do adversarial attacks. Like one of the most common is this Carlinian Wagner, or CNW. Basically, it minimizes the distance. As I said, this is like common between adversarial examples, and then it defines an adversarial loss F. That is basically, they showed several variations of that, like 7 variations, and they found that this specific one, I think the 6th one, is the one that showed the best performance. You basically take the difference between the limits of adversarial example, take the maximum, which is the second class. You take it from the maximum best class logit, and then you do some soft plus function on top of that, and this would be your adversarial loss. So you minimize this plus L2 norm between X and X plus delta. You do that minimization, you repeat it, let's say. So in this, there is another one, which is called, I think, PGD attack. But this one, it's all about how you would pick this C. So you repeat that several times until you reach to that adversarial example. But this picking this C, which is the trade-off between how close you are from the original image and how good is your adversarial example, can affect the accuracy and the success. So how would you measure how powerful is this adversarial example? We usually use the success rate, which is basically, if you are doing untargeted attacks, it would be the 1 minus accuracy. Like, how good is your attack? Basically, how much did it destroy the classifier? So which brings us to another type of attack, which is by Madri, and this is now kind of the standard, which is called the PGD attack. You basically project the output of the iteration into some specific set that surrounds X, and you do that iteratively. So this is a little bit different than this Carlini and Wagner. Here, you actually minimize the distance between X and X delta. Here, you don't minimize the distance. You just minimize the loss itself. You maximize the loss, which means you find the best adversarial example, and to ensure that this adversarial example is not too far from the original image, you do this projection step pi. You can do that in an adversarial training step, where you basically do this attack every time you want to train on any new image. If you do that during training, this is what's called adversarial training, and this is standard, like everyone do that. Here are some references. I'll not spend too much time on adversarial attacks because this is like a huge topic, but I think I just covered the main concepts on this. I don't know if you have any questions, just please interrupt me, because I'll jump into this paper. Any question? No?
Hello?
Yes.
Hello, Hamdi. Yeah, I want to know, I think the attacks which you have mentioned are white box attacks, where we know the model parameters
right.
and all.
Yes.
Yeah, I mean, can you explain something about the black box attacks as well? I mean,
This is,
because
this is a
recent
good,
papers.
yes.
Yeah.
So this is a good question. Actually, all what I showed here is white box attacks, which were the first to appear. There are another stream of work on black box attacks, basically that doesn't use any gradient information like this one. You cannot have this gradient if you have black box classifier. So in that case, it's more about how efficient are you to query your classifier, because you'd have to test, you have to do a lot of forward passes, either to estimate the gradient, estimate this term by doing 2 or 3, 4 forward passes, and then take the difference between the two outputs and divide by the amount, the difference in the amount between these two inputs. This will give you gradient or estimate of the gradient. You can do that, and there are other ways to do that. So actually the black box attacks is more spread. Like there are so many ways to do it. You can do it like in evolutionary algorithms. You can do reinforcement learning. I've seen papers do that. You can do query efficient. Somehow you smartly, some heuristics do to sample specific examples to reduce the amount of samples that you have to query in order to estimate the gradient or to attack the classifier directly. So this is not the focus. I will go over that. I think one of my papers is about black box attacks, so I'll discuss that in detail. So this ECV paper was, other question?
No, I just said thank you. Thank you.
Okay. So this paper is about adversarial attacks, extended it to 3D modalities. So there are a lot of papers right now doing adversarial attacks on NLP, like on BERT, or on other types of modalities like sound, or like any type of modality that deep learning exists. So this was about extending it to 3D point clouds. This was presented in this CSV as a poster paper. So 3D point clouds is a common way to represent 3D data. It's just X, Y, and Z, and it's a set of points. And this you can visualize this easily. It represents the object in a very sparse or very compact way. So deep learning have entered this point cloud realm in 2017 with the introduction of PointNet. It was the first successful deep learning framework that works directly on point cloud, and is used for 3D classification, 3D segmentation, and other stuff. And recently, some more of like graph networks or dynamic graph networks have entered the realm of 3D deep learning, and it's now very common. So if you look at the recent works, they always use some sort of concepts from graph convolutions to do point cloud processing. So the first paper that appeared on adversarial attacks was in CPR 19 by Xiang et al., where they basically perform a straightforward adversarial attacks. They showed several ways to do it. However, that first attack that appeared has several problems. It is very easily defendable, and you can see that the red or the perturbed point cloud is kind of sparse. You can see the effect of the attack. So if you actually do any smoothing or any like outlier removal, you can actually remove that attack. So it's a very weak attack. And it's very specific to the network. So if you attack, let's say, PointNet, you cannot, this will not transfer to other networks like PointNet++. So this is a common way to measure how strong is the attack, is to measure its transferability. So in images, people, for example, do the attack on ResNet and they see how it transfer to VGG or Inception and so forth. Another attack that appeared in IIII 20 was this attack where it's basically about smoothing the attack, which is, it uses the KNN laws that makes the attack smoother, and they 3D print 3D objects and then scan them, and they show that it is remaining adversarial. However, the attack there was not transferable again. So so this ICCV 19 paper was the first to do defenses. Like they proposed 3 defenses, outlier removal, random sampling, and this dubnet or denoising and upsampling network. And this is like a brief literature about this 3D adversarial attacks on point cloud. So in our paper, we basically aim to do adversarial attacks that are strong, which means they are transferable and they break all of these available defenses. And so this is the goal. We show actually that we outperform these previous attacks by up to 40% in terms of transferability, and we actually perform up to 38% improvement against these defenses, which makes our attack very strong, very transferable, and in real scenario, it's very dangerous. And this actually motivates the work to investigate more defenses and mechanisms to design robust 3D deep learning networks. So how do we do it? We basically use an autoencoder, AE, for point clouds, and we define a loss. We define 2 types of losses: a data loss and a typical adversarial loss, which was the one used by CPR 19 paper. We just add another loss, which is basically dedicated to focus on the data. So this loss is basically telling your attack to not only focus on the classifier, but also try to fool the classifier if the attack was recovered or cleaned by an autoencoder. So the way we combine these 2 losses is what's called ADVPC. So this is our objective. We want to minimize the distance in point cloud, not in images, between the adversarial point cloud and the clean point cloud. And we want to maintain a wrong prediction. Let's say if we are doing targeted attack to specific class label. And we also want the attack to be fooling even if we reconstructed the adversarial example by some G network, which is the autoencoder. This is the objective that we follow. It's basically a trade-off between adversarial example or adversarial loss on f of x bar and f of g of x bar. And we have one hyperparameter gamma that will do this trade-off. It's a convex parameter between 0 and 1 that will tell us whether to focus solely on the network or the reconstruction of the point cloud on top of that network. And we do this under the constraint that the distance between x and x bar should be less than epsilon p, which we call the norm budget. So we do like a PGD formulation, straightforward PGD formulation to update the perturbation. We call this perturbation delta. The projection we use is either like an L2 projection or an infinity projection. We use both in the paper, which is basically to limit the attack in the vicinity of the original point cloud. The distance we are using here is the L2 and the L infinity distance. This is like typical. And since our attack is additive, that means we are shifting the points. You can always measure the L2 and L infinity between 2 point clouds, just like what you do with 2D images. We experiment on ModelNet 40. This is like the ImageNet on 3D. Kind of everyone is using it for classification. We pick the classification task as the main, just like most before adversarial attacks work on. And here are some examples of the adversarial examples that we generate on 3D point clouds. You can see that this is like targeted attacks. You can see that you can, if, for example, this is PointNet or DGCNN, PointNet++. We basically pick the most famous 3D networks and we attack them successfully using our attack. These qualitative examples. Here are some quantitative examples. You can see that every row here is an attack on a specific network, like this is a victim network. And we do something called the transferability. So we want to measure transferability of these attacks. So we have two sets of network, victim networks and the transfer networks. Basically, what is the network used to evaluate the attack? You can see that if you used the victim network, PointNet, and you evaluate on PointNet, your attack will always be successful. So you can see the success rate is almost 100%. But once you move this attack to other networks, the success rate drops significantly. However, when you do our attack compared to these two baselines, we always get better success rate of the attack, which means our attack is stronger. You can see that, for example, here, it gets like 64, for example, percent success rate compared to 31 or 14 compared to the other two attacks. On the same setup, using the same norm budget epsilon infinity, for example, here. So we can plot this success rate versus the epsilon. And if you vary this epsilon, because this was done only on 2 epsilons, you can actually plot it on several epsilons. And this attack was performed using DGCNN and it was transferred to other networks. You can see that our AdVPC get always higher success rate than the other baselines, up to like 20%, for example, improvement, or here even 30% improvement. So this is like overall the attacks given all different 3D networks in the experiments. And you can basically summarize this in 3 transferability matrices, where we basically just average the success rate over the multiple epsilons and then report like victim network versus evaluation network. You can see that the success rate is always high at the diagonal for all the attacks. This is expected because when you attack the network and evaluate it on the same network, it would be the highest success rate. But if you move it to other networks, it would be lower. You can see that our attack is overall lighter. That means it transfers better between different networks. If you just take the average of all of the off-diagonal values, you get like 94.9, which is much higher than the previous attacks. So this number summarizes the entire results of the paper. We can also see how does it do on defenses. So here, for example, when you attack DGCNN, we try different defenses like that from ICCV 19, and we use like our own autoencoder, but if you train it again and with no defenses, you can see that our attack gets like higher success rate even on defended networks, and up to like close to 40% improvement sometimes on some specific defenses compared to the 2 other attacks. So this is an overall like idea of the paper. I can
Abdullah,
move to, yes. Please ask any question. Yes.
Yeah. So I was wondering. So for attacks on 3-point clouds, so what do you think the the perturbations are? Do they make the point clouds sparse, or what do they actually do? I mean, according to you.
So the thing is, these point cloud networks rely on the specific locations of these points. So you cannot know which point will affect the network unless you use this type of adversarial attack. It will know which point will be moved where, such that the whole classifier would fail. You can see this looks like a vase for you, but for a classifier, this is completely different. It changed completely. And these adversarial examples are just, so the black ones are the original one. You can see the blue look almost the same as the black one, but the prediction have changed from chair here, for example, to a vase, or from a chair to airplane, or and so forth. So it doesn't affect how we say it as a human, but for a deep network, this is completely different.
Okay, I see. Thank you.
Yeah. So we can move on to this paper. It was presented at IIII 20. In this paper, instead of looking at attacks on 3D directly, we attack the 3D by attacking the environment of a 2D images. So unlike these previous attacks that use pixel perturbation or pixel noise, what we want to do is something. We said, are these attacks meaningful, or can you explain? You just said these noises, like even in point cloud, they do not reflect anything that's useful or meaningful, let's say. And also, it's not very useful in a practical sense. So let's say we have noise that can be added to image and flip the network. How is that going to improve self-driving cars, for example? You cannot find a direct link to that, because these noises are artificial. It's created by hand or by gradients. It's not natural. So in this paper, we try to do adversarial attacks. We call it semantic adversarial attacks, which means the attack is not on the input level. It's on the parameters that define the image. For example, you can attack the image by changing the viewpoint of the image. And this will result in object detectors failing, for example. And we show like YOLO version 3, which is like one of the state-of-the-art or the fastest object detectors, failing here on detecting the object properly if you change the viewpoint for the same object. We also try it on self-driving cars and UAVs, and we show that if you change the track, for example, you can fool your self-driving or autonomous agent that was trained to move properly on this. So there was previous work in CPR 19 that's basically trying to, that showed that you can, the same object, if you just change its pose or distance, you can actually fool ImageNet classifiers with that. So this is just to say, this is not the only paper. There are currently, I think there are 15 published papers on the same topic in the last 2 years, including this one from CPR 19. So the main contribution, we describe a general setup for adversarial attacks that includes pixels and semantics. We propose BB-GAN, a GAN network that learns a distribution of semantic adversarial attacks. And we test it on 3 safety critical applications like object detection with YOLO version 3, Scala self-driving simulator, and UAV racing in Sim4Z simulator. Obviously, we cannot do real-life adversarial attacks in this way because we don't want to kill people. So this is all what we can do is test it on simulation. This is standard in RL field or other fields that work on like self-driving. So the general setup that we describe in the paper, we can say that any attack can be thought of as an adversary G. There was someone who is called G or adversary, that is observing an environment, that's observing an environment in which the agent lives. And then for every parameter u that's passed or given to the environment, we receive back a score q. And the adversary is trying, with time, is trying to give parameters u that are harder and harder, so that it will always receive lower and lower score. In the paper, we show that this works on, so that you can put this framework, it will fit the established field of adversarial attacks, where the agent is basically the classifier, and the parameter is the pixel noise. The environment is just a data set of images. However, it will also fit other type of adversarial attacks, like what we show here, where the agent is an object detector or a self-driving policy agent, a self-driving policy that's embedded in an agent A. And it can also be the parameters that describe the scene. For example, the camera pose, the light, the colors of the object, everything can be described by this U. And the environment can be a simulation environment, can be a data set if you're doing just classification. But it can be an interactive environment that basically give reward and observations to the agent. So this is our pipeline. We basically learn a BB GAN or a black box GAN. A GAN that's basically trying to learn the distribution of mu, such that your environment and agent will produce very low score at the end. The way we do it, we basically pass random noise or random parameters, and this is at the beginning, and we get we filter these parameters, we rank them according to their score, and we feed that as a training for the BB GAN. And we can do this in multiple iterations, such that our BB GAN will get better with time. And this GAN is not producing a single adversarial example, it creates a distribution of adversarial examples. And we show here some examples on this. So for object detection, these are the parameters that we want to attack, like the light, the distance of the camera pose, the color of the object. And here we show some adversarial examples generated by our BB GAN. You can see that this truck is not, the object detector is not able to identify these trucks. Even though if you change the color, it will be able to identify it. If you change the pose, it will be able to identify it. It sees it as a cell phone. So this is interesting. You can actually visualize these distributions. You can see that if you looked at the car from the back and the top, and the light was coming from the top middle, these setup will give you adversarial examples. So this is, you can imagine this is like a truck driving in the street. It has this specific setup facing it. It will not be able to detect the car in front of it. We actually test it in real life. So I have like a toy car, cannot do these types of experiments with real cars. I've just taken a toy car and I've tried to follow the same setup in the simulator. It actually transferred to real life. So this is like real actual adversarial examples. Here we show like the simulation, how the self-driving car is. I don't know if you can see the video. Can you see it properly?
Yes, yeah, we can see the video.
Okay, great.
Yes.
So here you can see how the BB GAN changed the weather, for example, and the camera angle on top of the car, such that the car failed. Here we show like how the UAV can drive smoothly, and this is trained to move in this on these tracks. But when you generate these adversarial tracks by our BB GAN, it creates tracks that are very hard for the AI agent to navigate. And it learns to create these sharp turns such that your agent would fail. We compare against some baselines in this, on these top 3 applications. We show that we can reach like very high success rate with this BB GAN compared to some methods like random, Gaussian, GMM, Gaussian mixture model, or Bayesian optimization, or GP regression, and so forth. these attacks are novel. So you can see that if you look at the training data, you cannot find a closest example to this. So this is generated attacks. You can see the closest example is not exactly the same. So it learned to produce adversarial examples that are new, that are not in the training examples, but still they work well in attacking the object detector, for example. This is the paper and the code for the paper if you want more details. If you have any question, please ask me before moving to the last paper in this in the discussion. Yeah.
Hello.
Yes.
Yeah, if you use techniques like data augmentation or like adversarial training where we use some different positions of the camera, can we defend this attack?
It's a good question. So I don't know if there are papers, there are attempts to do that. However, the problem is very difficult because you don't know before what is these angles. I mean, you can do like, you can basically get these adversarial examples and then train on this. But this will not solve the problem completely because you might be creating other angles and other positions that are adversarial. So this is an unsolved, it's an open research problem. How can you mitigate this? Or like this, for example, what they showed here in the CPR 19 paper. This is not an easy question. How to make AI agents that are robust to all sorts of variations it can face in the real world. This is one of the weaknesses of deep learning, and nobody really knows how to fix it. It's related to the problem of domain shift. And we know that deep learning doesn't work well when your test data is shifted a little bit from your training data. So yeah, this is an open problem. Okay, no more questions? I mean, we can have a brief discussion at the end. So this paper was from SCV again, but this one was a workshop paper at the Adversarial Robustness in the Real World workshop. It won the Best Paper Award at that workshop from SCV 20. And the organizers liked this paper. And the reason is, as I will show you, it has some math in it, I guess. But I think it was an interesting. So again, looking at these semantic attacks or attacks in the parameters that define the image rather than the pixels that define the image. So for example, this rotation of this teapot is slightly different from the rotation of this teapot. If you give me like state-of-the-art ImageNet classifier, it has a teapot class in it. It will give this image a confidence of 99.89 that this is a teapot, but it will give a confidence of 0.01 that this is a teapot for this image, like a huge difference. And you can actually just rotate this specific object and observe the softmax value of different networks that are trained on ImageNet, like ResNet, AlexNet, VGG, Inception version 3. And you can see that the confidence varies, actually drops almost to zero in some angles. Even though for a human, if you look at this, you would see it as a teapot from all angles, everywhere. You cannot be fooled from this. So this actually motivated this study. It was mainly focused on ImageNet classifiers, that everyone is using them as a backbone in most of the tasks. And we show that it's actually very dangerous. So this is the analysis paper. We try to analyze the network. We have like a differentiable parameter, and we have a 3D object that the network can identify. We want to analyze this network by changing the parameter space. we plot what we call semantic maps, basically showing, just like this plot, we call this semantic map, or how the confidence of the network varies with different semantic parameters. So we collect 100 shapes from 10 different classes from ShapeNet. We filter these shapes such that the ImageNet classifiers can identify them on average. So these are shapes from ShapeNet, but those are identified by ImageNet classifiers. And then we start plotting these maps. We basically start rotating. We pick two parameters, which are of interest to this paper, which are the azimuth and the elevation angle of the camera looking at the 3D object. And then we observe how the confidence of the network varies. We can see that if we looked at the confidence of the network, you rotate the object from all angles, you see that the confidence actually fades away from specific angles. If you look at the object from the bottom, obviously you will not recognize it, which is fine. But you can see, even if you look at the top, there are some angles that are very hard for the network. We show here what we call these semantic maps for different networks on the same objects. You can see even between networks, they vary considerably. Like Inception and ResNet have very different response to the same parameter, with the same object, with the same training data. And here, for example, the cup. You can see that it's symmetric, and that's because if you look, these objects are by design. People design these objects like chair, cup, or TV, such that they're symmetric. If you look at it from the left or the right, it will give you more or less the same image. That's why you get the same response from different symmetric angles. But there are some angles where it suffers, even for a simple object like a cup. And this is what we call semantic traps. Basically, when your network is confident everywhere, and in the middle there is some red dot, or confidence drops to 0, this is very dangerous. If this is a car and you think it's doing well overall, because the average here is always blue in this region, however, there is a red region in the middle, we call this trap, because the network would fail even though you would think it will work well. The problem with these analysis, it's very expensive. To plot this, we have to do a forward pass in every pixel in this map. And this is very expensive. Imagine you have, we estimated you need to do like 10 to the power 18 forward passes if you have 8 parameters, for example, to fully map the network. So what we do in this paper, we propose a bottom-up approach. Basically, given a network, and given an object, you want to analyze the performance of the network starting from specific parameters. We want to find the region where the network behaves robustly. We define robustness here to have a high confidence, so the expected value is closer to 1, and the variance is closer to 0. That means it's very confident and it's very constant on this region. And to do this, we want to maximize this region D. We want to find the maximum region D such that the confidence is high and the variance is low. And to do that, we do this in an optimization way. So we basically measure the region, or we want to maximize the area inside the region such that the confidence is high. But if we do that, the region will just grow to infinity. And to limit that, a naive way is just to add a regularizer on the region area. So you can minimize this objective. And the gradient would basically look like this. You take the gradient of the function. The function f is basically this pipeline that I showed earlier. This is the function f. It's the confidence of the network for a specific parameter u. So, sorry. So we propose 3 ways to optimize these bounds to find the robust region in the semantic space, a naive way or an outer inner ratio black box way. So this works on black box, you don't need the gradients. And this one is a white box way where you have access to the gradients of the network, G. So F is forward pass, G is the backward pass of the network. And we find these formulas to update the bounds of the region. You can see that, for example, starting from any point, you can find the robust region of the network using this specific optimization. And here we show how these optimizations converge to objects or areas in the semantic space that covers robust regions. One application of this is basically to quantify semantic robustness of these deep neural networks. And the way we do it, we run several algorithms, or we run this algorithm several times to find the expected volume of this robust region. And then we normalize it by the total volume of the semantic space. We get a metric, we call it server, or what's it called? Semantic robustness volume ratio. This gives you an estimate of the semantic robustness of the network. And one observation of this paper is that this server metric gives ResNet the highest robustness, even though it is much less in terms of accuracy compared to Inception version 3. So it's less accurate. For example, the top one error is like 23.85 compared to 22.55 to Inception, but the server is much higher than the Inception. That means it's better or more robust than Inception. This observation, I think this is the first paper to point out this observation, and we actually we would like to investigate this more. So we ask people to investigate this more. We publish the code and the models and the algorithms on GitHub. And another application is basically to visualize the data bias in your data set. So if you look at these maps and you just average them for the entire class, you can get an estimate of how the data bias of the cup class on ImageNet. You can see that most of cup classes on ImageNet follow specific distribution. And this gives you an idea of how the data look like in terms of the semantic bias. So this is the code online. It's in PyTorch. Feel free, please, to try it out for yourself. This brings me to the end of the presentation. If you have any questions in general or on this specific paper, please let me know. Sorry.
Hello.
Yes.
Hi, Abdullah. I think it's a nice presentation overall. I have this question on attacking the data such that YOLO v3 detects, the object detector detects one class as another class. You have shown some examples, right? Yeah. Hold on. Yeah. So in this, is it the case that the object detector always identifies, always detects an object, or will there be cases that it not even detects an object at all? That is question one.
There are, so it's not question mark. If you are familiar with object detection, you have a threshold. You control this threshold. If you allow this threshold to be very low, it will detect a lot of objects. So people usually set it to 0.4 or 0.5. So if you set it to 0.5 during test time, sometimes you will not detect any object, even though the object is there. So we consider this as a success for the attack. Sometimes you detect it, but with the wrong class, like this one. So we consider this also as a success for the attack. If you detect the object with the correct class, which is struck, that means the attack didn't work.
Yes, so yeah, so in that case, how is the success rate defined in this case? Is this there is a
So the
trade-off between
success
the
rate, yeah. So
threshold?
the success rate is defined on how many examples that were not correct. How many examples the object detector was not able to detect the object with the correct class label. And you can see it from the, I think we put it the table there. Yes. So if you look at this success rate overall, the average on 12 classes that we use in this paper, you can see if you use just random noise or like, yeah, if you use random noise, like you can fool the object detector like 45% of the time.
Yeah, I got it. Thank you.
But using this BB GAN, you can get it like up to 80% adversarial, which means like with every 10 examples, 8 would be adversarial.
Thank you.
Yes.
So, Abdullah, a small question. For the ones that you changed the lightning and all those weather conditions. So, I mean, did you try and test for the transferability of these attacks for domain adapted learning?
So yes, as I said, this problem is related to domain adaptation, and people are investigating this on semantic segmentation, specifically when you change the weather, for example. And
Exactly, yeah.
So they usually use a sort of cycle GAN or something to transfer the domains to the original domain, and then they do the segmentation. This is one way, but this will not solve the issue completely. In this paper, we tackle the problem in a general setup. So it's not specifically the weather. As I said, like if you look at the formulation, any environment with any parameters that affecting the environment can be thought of as someone is trying to fool your classifier by perturbing this environment. So yeah, there is interchange. There is a relation between adversarial attacks and domain adaptation. And in this setup, it's even more clearer than the setup of this, for example. Even though even this one, you can think about it as domain adaptation, because when you add noise, you change the domain of the image. So yeah, you can do that, domain adaptation techniques, but you can do even robustness techniques like adversarial training. And until now, there is no correct way doing stuff. It's an open research problem for both robustness and domain adaptation.
I see. Okay. Okay. Got it. Yes.
Yeah.
Hi, Abdullah.
Yes.
So, my question is, in the last paper, you showed that even if we change the orientation of an object by some degree, the classifier fails. But so,
Yes.
in your opinion, what is actually the problem? Is it something related to the data set that there were no images uh, relating to that, or some other problem with the model itself?
So I believe it's a combination of both. First of all, the data, and there is also the network training effect. If your network was trained in a specific way versus if you trained the network in another way, this effect might be different. And we showed how, for example, ResNet is compared to Inception. You can see, for example, yeah, this one. You can see how Inception and ResNet, they are trained on the same specific data set, which is ImageNet, but they have different response. So Inception have high confidence here, ResNet is more smooth, so it doesn't have high confidence here, but it has red, but it's overall smooth. So yeah, it's not only the data, it's a combination of data and the network training.
All right, got it.
Okay. Any other example
Any other question,
or
guys?
other question? Yes. Yes, please. Hello.
Yeah. Any other question, guys?
Oh, okay.
Yeah. Sorry, I was asking it up.
Yeah.
So another question. In the first paper, you measure the transferability of your attacks. So what I understood is even if it is a white box attacks and it's very transferable,
Yes.
it can behave as maybe a black box attack.
Exactly. So it is black box to the other networks. It has not seen the other networks, so it's black box to the other networks. It's white box to the victim network.
Right. Okay.
Yeah, it is. So it is transferable. That means it works as a black box attack very well to other networks. And this is one use case of these transferable attacks. Um, yeah, I mean, if we don't have any other questions, we can conclude. We can conclude, I guess.
Yeah. I think we are already like 6 minutes past the
Yeah.
time. Like,
So,
if there are any last questions, yeah, like feel free
there are
to
not
ask.
a question related to your current work. So I mean, a lot of people around here are really wondering about, uh, I mean, how your culture at KAUST is, because we don't have much people talking about these. I mean, your areas of, I mean, colleges and culture around there. So maybe if you can brief us a little bit more about it,
I mean, culture. Okay, so KAUST is not similar to any other place in Saudi Arabia, even though it's in Saudi Arabia. It has like a very good campus. I mean, you can search on Google or YouTube. You can look into that, but it's very friendly. So so there are 200, I think, nationalities in KAUST, which is, I think, the largest, or 160, the largest in the world in terms of a single campus to have nationalities like that. And the percentage of international students is, I think, 70% or 60 to 70%. So this is like, I think, also a record in the entire world. So this is like a very unique university, I would say. Um, it is very well funded, and like research is the main goal. So there are no undergrad students in the university. It's only master and PhD students, postdoc, and research scientists. So it's like it very focused on research. Um, there are a lot of Indians in KAUST, so I think if you, probably not everyone in the world knows it, but whenever I ask an Indian about KAUST, they say yeah, they know it, and they know somebody in there somehow. This is very weird.
that's a nice thing to actually know about.
Yeah. Actually, it's
So yeah.
good to talk to people from IIT. Also, I actually met. So initially, I thought IIT was one university until I met somebody from ICCV. I met him like in ICCV, and he was telling me like, "Oh, I'm from IIT." I said, "Oh, cool." He told me like, "Oh, but there are like 23 IITs, and yeah, not all of them are the IIT that everyone thinks they are." But I looked at like the ranking, and Hyderabad is one of the top, I think, the top 6 or the top 7 IIT in India, which is very great. So you're also in a unique place.
Yeah, I'm sure. Yeah, this is like very true about our place. So
Are you guys PhD students, master students, or undergrads?
I think we have a robust distribution out here. So it's like PhDs, MTechs, all of them are like collaborative and kind of groups and all. So that's how things are out here.
Great, great. So you have PhD programs in IIT Hyderabad?
Yeah, definitely. I mean, it's like a very looked forward and sought to program out here. So,
Great,
so,
great.
so I think if we
Yeah,
don't have any more questions, so let's wait for one more minute if people can turn up.
sure. By the way, thank you guys, Sorgan and the rest, for organizing this. It's very good. I mean, for me as a PhD student to receive invitation like that, it means a lot for me because I don't receive invitation to talk about research very often. So when it happens, it's very unique. And this is the second time I was invited by also an Indian group to talk about research. So yeah, it seems people in India like my work on adversarial attacks.
Yeah, I think your work is very uniquely positioned about 3D point cloud attacks. So we see a lot of rare my groups actually working on this problem. So that's how we were
Yeah, it's
encouraged
very
to.
new. So when I started working on this, there was no paper or no one was working on that, and all of a sudden everyone started working on that. So yeah, if you look at ICCV, ECCV, CPR, iClear, you see at least 3 papers doing these sort of things. Now every round you see at least 3 papers that do more or less similar stuff.
I see. Yeah. Yeah, I guess its saturation point is far away to come.
Yeah. Yeah, so if you're interested in working on adversarial attacks, this is one way to go. It's investigating these semantic attacks or 3D adversarial attacks. And this is relevant to autonomous driving, which has a big industry like Uber, Tesla, and all of them are interested in autonomous driving. So this is the closest thing in adversarial attacks to or robustness to these big companies working on self-driving cars.
Hello.
Sure. Yeah.
Yes.
Yeah, I think it is just again off topic. I think it's again becomes a cycle of one guy presents and comes up with a defense, and other guys try to make a robust attack to the defense. So it keeps on cycling the way this area is emerging, I think.
Yeah, there is another way of doing what's called certification. Basically, you have a proof that no attack can attack from with a specific range within the image. This is also a new type of research called certification, and there are people working in my group on this, like randomized smoothing and all of that. So this is another type of way that doesn't have defenses and attacks, but you have certification. You say no matter what you do within this range, you cannot flip the decision of the classifier.
Okay, yeah, that's a new thing we got to know.
Yeah, this is a new, maybe just 2 years it started, or 1 year, even last year it started. And now every round you see 2 or 3 papers. If you Google the term randomized smoothing, you see like 2 papers every round talking about this.
Okay, thank you. Yeah.
Yeah, thank you, Naveen. Okay, I think we can conclude. Surgan?
Yeah, I think so. Yeah.
Yeah, definitely. I think, I mean, thanks for joining in today and talking about your 3D attack work. So I think there are a lot of people who I mean, asked a couple of questions. So, I mean, is it fine if someone who has like questions after recording reach out over mail or something like that?
Yes, you can find like in the announcement there was my Twitter account, my GitHub. You can always reach me by email or by if you go to my website, you will find my email, my contact numbers. You can reach me directly if you have anything you want to tell me. If you want to ask anything about KAUST, please feel free to reach out to me. And please tell your friends about this work, or about KAUST in general. Maybe some people want to come to study PhD at KAUST. Let them know about this.
Yeah, definitely. I mean, I think the colleges, universities from Middle East are actually doing well, considering Technion and all those things. But still, there is a lot of, what do you say, apprehension for people out here to go and join those universities. I mean, we do not have actually contacts over there, so I think that's
There is
that's really
no,
gonna help.
you don't need a contact. You have to apply. If you get accepted, you are sponsored by KAUST. So it's fully sponsored. You don't need any money. You don't need any contact. All what you need is good profile, good CV, and a master degree if you want to do PhD. If you want to do master, you need a bachelor degree.
Okay, I see. I guess we can conclude. Okay, yeah.
Okay.
So thanks again for coming.
Yeah, thank you, everyone. Okay, everyone. Nice to meet you, and see you soon, probably in next meetings or anywhere. Maybe.
Nice to meet you.
Okay. Have a nice day.
Thank you.
Have a nice.
Yeah.